So, what is quantum physics? Before I explain what's quantum physics, let me start at a little bit lower level. Let's start with the physics before the quantum physics, which we now understand as Newtonian physics or classical physics. So, what is Newtonian physics? Isaac Newton was a physicist who created modern physics, and his physics is known as Newtonian physics or classical physics. This physics is based on very simple idea of having a material body, an object with some mass and some forces being applied to that body, and we are interested in determining the motion of that body. What is the acceleration or the velocity of that body once the force is applied? Force equals mass times acceleration. This is Newton's second law of motion, the famous Newton's second law of motion, which is at the heart of Newtonian physics. So using this just simple equation, literally thousands and thousands of problems can be solved, and the world that we see around us, the world, everyday world of people moving, or cars, or just throwing some object some distance, or turning a wheel, all these examples, they involve Newtonian physics. So we don't need quantum physics for that, because Newtonian physics is quite sufficient for that. But it turns out that as the size of a body is decreased, okay, and is decreased to very small levels, to the level of a nanometer. Now we know what nanometer is. Nowadays they talk about the transistors. The microchips have transistors of nanometer geometry. So nanometer is 1/1000th of a meter. So when we get to that level, something very interesting happens, and the Newtonian physics begins to break down, and one has to talk about in terms of quantum physics, and the quantum phenomenon come into existence. So what is a hallmark of a quantum phenomenon? Okay, at the quantum level, it doesn't make any sense to say that an object is in one place or the other. This is what we understand from the world around us, that an object, for example, this book or this cell phone is sitting here, and I know exactly where it is sitting, or where I'm sitting, or whether you're sitting, or whether you're walking, or you're not walking, you're stationary. So in classical physics, the location of an object is precisely described, is precisely determined. But this is not true in quantum physics anymore. So a quantum object can never be in one place. Its position, it cannot be determined precisely. And the reason for that is something known as Heisenberg's uncertainty principle. Heisenberg was one of the founders of quantum physics, and he gave this principle known as Heisenberg's uncertainty principle, which says that the position and the speed of a body, okay, they are complementary quantities. Complementary in the sense that if you measure one very precisely, then the other one becomes uncertain. So if you measure the position of a quantum object, such as, for example, an electron, then its speed, actually the actual scientific term is momentum. Momentum is defined as mass multiplied by velocity. But for the sake of discussion, we can say motion or speed. Then that becomes uncertain. And if you can precisely measure one, then the other one becomes extremely uncertain. Okay, it becomes so uncertain that it doesn't even make any sense to talk about that anymore. So this is the boundary between the classical physics and the quantum physics. The Heisenberg's uncertainty principle determines that when you get to a scale where the system has become so small and so light that, of course, the size and the weight of the mass, okay, the mass and the size of the object, these two quantities determine when we transition from the classical world to the quantum world. So in the quantum world, things are very, very different from the way we understand the things in classical world. For example, I just described that in classical world, a thing is either either stationary or moving, and its location is precisely known. In quantum world, we can never tell whether this thing is standing still or moving, and its position cannot be determined precisely. And there is another way in which quantum physics differs very much from the classical physics. In classical physics, there are two different types of phenomena that physics studies. One is the particle, another is the wave. We understand what a particle is. And the other form in classical physics, which is quite important, I just described the particle nature. There is another one called the wave nature. So the phenomenon in the wave nature domain are very well known to us. The sunlight that we see streaming through our window is a wave. So I'm sure everybody has seen this spectrum of sunlight going through a prism. You let the sunlight fall on prism and you see 7 colors. So that is wave phenomenon in classical physics. So, and Newtonian physics describes that very well. So we have two phenomena, two very different phenomena. One is particle nature and one is the wave nature of an object, of physical phenomena. So there are two physical phenomena, the particle and the wave. Any object can be considered to be a particle in Newtonian physics. All we need to care is the mass. So the dimension, the geometry of the body is not very important. So for the sake of discussion, this book could be considered to be a particle in classical physics. But in quantum physics, the particle and wave distinction disappears. So this is an artificial distinction between particle and wave as far as quantum physics is concerned. So the concept of duality comes into being. So what is duality? That a quantum object has dual nature. It is particle and wave at the same time. So one cannot say whether an electron, let's take an example of a quantum system. Electron is the perfect example. So we cannot say whether an electron is a particle or a wave. So what quantum physics tells us that you have to assume it's both at the same time. And this duality property is encoded in a mathematical function known as wave function. So the wave function is one of the most important quantities in quantum physics. To study a quantum phenomenon, we need to determine its wave function. And that wave function has all the properties of that quantum system. Its particle nature, its wave nature. So let's take, for example, electron. Electron is a subatomic particle. All atoms are made of electrons. So we are made of electrons. Biology is mostly concerned with electrons. Chemistry is also mostly concerned with electrons. In physics, of course, there are multiple subatomic particles and electron is one of them. But for everyday life, all the objects we see around us, including human bodies, biology, life, it's mostly concerned with electrons. So electron in quantum physics is a quantum object, so it has dual nature. It is both particle and wave at the same time. So the particle nature of electron can be understood by thinking of this old-fashioned television. If you remember, in the old days, televisions used to be as thick as they were wide. So in those television sets, there was an electron beam that was produced at the back of the television by an apparatus, and then that electron beam would come and strike the screen, and that's how the picture was generated. So their electron is behaving like a particle. So the moment the electron hits the screen, one electron hits the screen, it creates a bright dot of light, and that's basically where that electron hit the screen. Now it turns out, and this is very interesting, electron also shows wave-like properties, and these can be demonstrated in a laboratory using an apparatus known as double-slit experiment. So those of you who have taken some physics courses, you know what a double-slit experiment is. You let light pass through a slit, a very small slit, and then you let it fall on two slits, very, very thin slits, and you see an interference pattern on the screen on the right-hand side. So if the light is coming from left-hand side after passing through double slit, because of the interference between the light waves that are coming from the slits, you see an interference pattern. Interference pattern is nothing but a pattern of light and dark stripes of light on the screen, you'll see that instead of the screen being lit uniformly by that light that's coming, you'll see alternating stripes of light and dark, light and dark. So this is an interference pattern of a double slit experiment. So such an experiment can also be repeated using an electron beam, and just like light, it also shows light and dark stripes, except that you need a television screen to see that. So you let that pattern fall on a television screen, like a screen like a television screen, what we call electroluminescent screen, and you can see the same pattern. So there we see that both the wave nature and the particle nature of the electron are being clearly demonstrated. So what I just said, what I covered two major topics. What is quantum physics? Quantum physics begins where the classical physics ends, and the boundary between the classical physics and the quantum physics is the Heisenberg's uncertainty principle, which is a principle that relates two quantities, the position and the momentum. It actually relates the uncertainty between the position and the momentum. So more certain the position, more uncertain the momentum, or the other way around, more uncertain the position, more certain the momentum. So this is what Heisenberg's uncertainty principle says, and the duality, which is the wave particle that we see in the everyday world, it's basically it disappears. And in quantum physics, wave and particle are not two different things. They coexist together, and the information about the wave and the particle nature of a quantum object is encoded in this mathematical function known as wave function. And whether that quantum object is going to reveal itself to us as a particle or a wave is determined solely by the experiment. Okay, so this is very different. This is very interesting. In Newtonian physics, it doesn't matter whether you conduct an experiment or not. The behavior of the object is not going to change. If I apply a certain amount of force on this book, it's going to move, and depending on my force, I can determine how far it's going to move and how fast it's going to move. But in quantum physics, it's the experiment that determines the end result of what you did to the quantum object. This is very interesting. Okay, so that's another way the quantum physics differs from the classical physics. There are many other differences. I'll cover them in my future lectures, but for the time being, we can stop here, and in the next lecture, I'll cover more interesting aspects of quantum physics. मेरा ये लेक्चर अंग्रेजी में था क्योंकि क्वांटम फिजिक्स किताबें और सारे साइंटिफिक जर्नल्स और नॉलेज जो है वो अंग्रेजी में है, पर मैं इसको हिंदी में भी बोल सकता हूँ, मुझे हिंदी बहुत अच्छी आती है. तो अगर आप चाहते हैं कि मैं ये लेक्चर हिंदी में रिपीट करूँ तो कमेंट सेक्शन में लिखिए, और मैं ये लेक्चर हिंदी में रिकॉर्ड करके आपको प्रेजेंट